Hello, my name is Ajay 18 BCE 2332. My subject is network and communication. My topic is interplanetary internet. The interplanetary internet is a conceived computer network in space, consisting of a set of network nodes that can communicate with each other. Interplanetary communication is greatly delayed by interplanetary distances, so a new set of protocols and technology that are tolerant to large delays and error are required. The interplanetary internet is a store and forward network internet that is often disconnected, has a wireless backbone fraught with error-prone links and delays ranging from tens of minutes to even hours, even when there is a connection. Development in interplanetary internet. Space communication technology has steadily evolved from expensive, one-of-a-kind, point-to-point architectures to the reuse of technology on successive missions to the development of standard protocols agreed upon by the space agencies of many countries. This last phase has gone on since 1982 through the efforts of the Consultative Committee for Space Data Systems (CCSDS), a body composed of the major space agencies of the world. It has 11 member agencies, 28 observer agencies, and over 140 industrial associates. The evolution of a space data system standard has gone on in parallel with the evolution of the Internet, with conceptual cross-pollination, with fruitful but largely as a separate evolution. Since the late 90s, familiar with Internet protocols and CCSDS spacelink protocols have integrated and converged in several ways. For example, the successful FTP file transfer to the Earth-orbiting STRV-1B on January 2, 1996, which ran FTP over the CCSDS IPv4-like Space Communication Protocol specifications SCPS protocols. Internet protocol use without CCSDS has taken place on the spacecraft. Example: demonstrations on the UOSAT-12 satellite and operationally on the disaster monitoring constellation. Having reached the era where network and IP on board spacecraft have been shown to feasible and reliable, a forward-looking study for the bigger picture was the next phase. The Interplanetary Study at NASA's Jet Propulsion Laboratory (JPL) was started by a team of scientists at JPL led by Winton Cerf and the late Adrian Hook. Cerf is one of the position of distinguished visiting scientists at JPL. Hook was one of the co-founders and directors of CCSDS. While IP-like SCPS protocols are feasible for short hops, such as ground station to orbiter, hover to lander, lander to the orbiter, probe to flyby, and so on, delay-tolerant network is needed to get information from one region to solar system to another. It becomes apparent the concept of region is a natural architectural factoring of the interplanetary internet. A region is an area where the characters of communications are the same. Region characters often includes communication, security, the maintenance of resource, perhaps ownership, and factor. The interplanetary internet is network in a network regional internet. What is needed then is a standard way to achieve end-to-end communication through multiple regions in a disconnected variable delay environment using a generalized suite of protocols. Example of the regions might include the terrestrial internet as a region on the surface of the Moon or Mars, or a ground-to-orbit region. The recognition of the requirement led to the concept a bundle as high-level way to address the generalized store and forward problem. Bundles are an area of new protocols development in upper layers of OSI model above the transport layer, with the global addressing the issue of bundling store and forward information so that it can reliably traverse radically dissimilar environment, consulting a network of region internet. Delay-tolerant networking (DTN) was designed to enable standardized communication over long distances and through the time delays. At its core is something called Bunty Protocol (BP), which is similar to the Internet Protocol or IP that serves as the heart of the Internet here on Earth. The big difference between the irregular and regular Internet protocol and the bundle protocol is that assumes a seamless end-to-end data path, while BP is built to account for errors and disconnection glitches that commonly plague deep space communications. Bundle service layering, implemented as the bundle protocol, suited for delay-tolerant networking, which provide general-purpose delay-tolerant protocol services in support of a range of applications, custody transfer, segmentation and reassembly, end-to-end reliability, end-to-end security, end-to-end routing among them. The bundle protocol was first tested in space on the UK DMC satellite in 2008. An example of one of these end-to-end applications flown on a space mission in the CCSDS Files Delivery Protocol (CFDP) used on the Comet mission Deep Impact. CFDP is an inter-standard for automatic reliable file transfer in both directions. CFDP should not be confused with Coherent File Distribution Protocol, which has the same acronym and is an IETF documentation experimental protocol for rapidly developing deploying files to multiple targets in a highly networked environment. In addition to reliably copying a file from one entity, such as a spacecraft or ground station, to another entity, CFDP has compactly to reliably transmit arbitrary small messages defined by the user. In the meta accommodating accompanying the file, and to reliably transmit commands relate to file system management that are to be executed automatically on the remote endpoint entity, such as spacecraft upon successful reception of file. Protocol: The Consultative Committee for Space Data Systems (CCSDS) Packet Telemetry Standard defines the protocol used for the transmission of spacecraft instrument data over the deep space channel. Under the standard, an image or the other data sent from spacecraft instrument is transmitted using one or more packets. CCSDS packet definition: A packet is a block of data with length that can vary between successive packets ranging from 7 to 65,642 bytes, including the packet header. Packet size data is transmitted via frames, which are fixed-length data blocks. The size of a frame, including frame header and control information, can range up to 2048 bytes. Packet size are fixed during the development phase because packet lengths are variable but lengths are fixed. But boundaries usually do not coincide with the frame boundaries, telecom processing ones. Data in a frame is typically protected from channel errors by error correcting codes, even when the channel errors exceed the correction capability of the error correcting code. The presence of error is nearly always detected by the error correcting code by a separate or error detecting code. Frames for which uncorrectable errors are detected are marked as unconceivable and typically are deleted. Handling data loss. Deleted undecodable whole frames are the principal type of data losses that affect compressed data sets. In general, there would be a little to gain from attempting to use compressed data from a frame marked as undecodable. When errors are present in a frame, the bits of the subband pixels are already decoded before the first bit error will remain intact, but all the subsequent decoded bits in the segment usually will be completely corrupted, as a single bit error is often just as disruptive as many bit errors. Furthermore, compressed data usually are protected by powerful long block length error correcting codes, which are the types of codes most likely to yield substantial fractions of bit errors throughout the frames that are undecodable. Thus, frames with detected errors would be essentially unusable even if they were not deleted by the frame processor. The data loss can be compensated for the following machines. If an enormous frame escapes detection, the decomposer will blindly use the frame data as if they were reliable, whereas in case of detected enormous frames, with decompressor can base its restructuring on incomplete but misleading data. However, it is extremely rare for an enormous frame to go undetected. For frames coded by the CCSDS Reed-Solomon code, fewer than 1 in 40,000 enormous frames can escape detection. All frames not employing the Reed-Solomon code use a cyclic redundancy check (CRC) error detecting code which has undetected frame error of less than 1 in 32,000. The implementation of interplanetary internet. The Interplanetary Internet Special Interest Group of the Internet Society has worked on defining protocols and standards that would make the IPN possible. The Delay-Tolerant Networking Research Group (DTN-RG) is primary group researching delay-tolerant networking (DTN). Additional research efforts focus on various uses of the new technology. The Canceled Mars Telecommunication Orbiter had been planned to establish an interplanetary internet link between Earth and Mars in order to support other Mars missions. Rather than using RF, it would have used optical communication using laser beams for their higher data rates. Laser comms sends information using a beam of light and optical elements, such as telescopes and optical amplifiers, rather than RF signals, amplifiers, and antennas. NASA JPL continued to test the DTN protocol with their Deep Space Impact Networking DINET experiment on the board Deep Impact EPOXI spacecraft in October 2008. In May 2009, DTN was deployed to payload on board the ISS. NASA and Bioserve Space Technology, a research group at the University of Colorado, have been continuously testing DTN on two commercial generic bioprocessing apparatus (CGBA) payloads. CGBA-4 and CGBA-5 serve a computational and communication platforms which are remotely controlled by Bioserve's Payload Operation Control Center (POCC) in Boulder, CO. In October 2012, ISS Station Commander Sunita Williams remotely operated mock-up Metron operations and communication prototype, a cat-sized Lego Mindstorm robot fitted with a BeagleBoard computer and webcam, located in the European Space Operations Center in Germany in an experiment using DTN. These initial experiments provide insight into the further future missions when DTN will enable the extension of the networks in the deep space, explore other planets and solar system points of interest.